All right, and welcome back, everyone. We are the smart. We are so pleased to have every one of us on the call. I know that more people will still be joining us as we proceed, but there's a need for us to move forward from here. I am your wonderful moderator for today, Oyeban Jodwan Samuel, an intern at Energex Research Center. Please, if I'm audible, we can kindly react by just giving me a thumbs up so I proceed. All right. Thank you very much. Thank you, Mr. Ismail Adetola Shito. Is one of our wonderful participants for every of our webinar, and he has always been timely. I think we'll prepare something for you in the future. Thank you very much, sir, and welcome back to another Smart Conference webinar. As we all know, and as we've already stated, this is what it is, a pre-conference webinar ahead of what ahead of the Smart Conference themed energy transition, which is going to be happening from October 18th to October 21st, 2026. So before the conference, we've had series of webinar ranging from research to reality, and now we are undertaking the series energy management. During the from research to reality series, we were opportune to have an hydrogen energy discussion, and we are so blessed again because this time around we are even delving deeper into what more discussions around hydrogen as well as an energy carrier. And I'm sure that this should give every one of us a signal, most especially academians amongst us, researchers amongst us, and engineers amongst us. And it should help us envision the possibility of what implementing the hydrogen energy into what Africa's energy discussion, Africa energy movement and team. And for the wonderful webinar today, we have our Dr. S.A. Sharif, who is a professor, and I'm going to read his professional summary. I'm going to go on to tell us about his education, his research and teaching expertise, and his academic leadership and what editorial roles to bring us all in the wonderful light of who he is. He's an incredible fellow, and he has done incredible work in the area of what hydrogen as an energy carrier and its application in what in the transportation industry. So, who is Dr. S.A. Sharif? He's a distinguished professor of mechanical and aerospace engineering and with an extensive career dedicated to thermal and fluid sciences. Is a globally recognized expert in thermodynamics, heat transfer, and energy systems. Dr. Sharif holds prestigious fellow and life fellow status across multiple premier engineering societies, including ASME, ASHRAE, the Royal Aeronautical Science, and ASTFE. Is a prolific researcher and author, serving in top editorial roles for leading international journals and driving forward advancements in sustainable energy, cryogenics, and spacecraft thermal management. So this is just a professional summary of Dr. Sheriff, and I know that we all by now we are all amazed, we are all awed by the person we have on board with us today. So in terms of education, he got his PhD in mechanical engineering from Iowa State University in the year 1985. Now that's just a summary. So for research and teaching expertise, Dr. Sheriff research spans critical area of thermal transport, fluid dynamics, and energy optimization, um, ranging from topics such as heat and mass transfer and thermodynamics, thermal system design and optimization, refrigeration, cryogenics, and HVAC, and so on. Now, as an academic leadership and editorial roles, Dr. Sharif is deeply involved in the global engineering community, sharing the dissemination of technical knowledge through extensive editorial leadership. He was editor-in-chief for the ASME Journal of Thermal Science and Engineering Application from the year 2014 to 2019, and ASME Journal of Solar Engineering 2020 to 2028. So he's still presently serving as what the Journal of Solar Energy editor. Now, for as an associate or guest editor, he was an associate or guest editor for the International Journal of Hydrogen Energy, Solar Energy, ASME Journal of Transfer, Springer Nature Energy Report, and the Philosophical Transaction of the Royal Society, London, amongst other. Now, serving as an editorial board member, he serves on the board of 25 additional journals in thermal, fluid, and energy sciences. Now, in terms of leadership, who is Dr. Sheriff? So, is a vice president of Commission B2 of the International Institute of Refrigeration, board of directors for the International Association for Energy, Hydrogen Energy, and the founding member and VP of programs for the American Society of Thermal and Fluid Engineer. That's ASTFE. By now, I think we should have reactions rolling in. These are not a profile that we come in contact with every day, except you are, you know, thank you. So, professional fellowship. So, is a life fellow for the American Society of Mechanical Engineers for the year 2000. A life fellow again, American Society of Heating, Refrigeration, and Air Conditioning Engineer, 2002, and Royal Aeronautical Society, 2017. A fellow American Society of Thermal and Field Engineering, 2023, and X and Aeronautics. That's Total Society of Engineering Education. Wonderful. That's actually exemplary words. Wow, we are spending time, right? On his notable awards and honor, Dr. Sheriff has received numerous accolades for his service, teaching, and contribution, including the ASME Dedicated Service Award in the year 2026, the ASME e-Transform Memorial Award in the year 2025, the ASME Frankfurt Energy Award in the year 2024, the ASME e-Transfer Division 75th Anniversary Medal in the year 2013, the ASHRAE Exceptional Service Award the year 2010, and Distinguished Service Award the year 2003. Oh, if I go on, we will be amazed, right? If think it's over, right? It's not yet over. He has notable award for the AIAA and the ASME Best Paper Award in the year 2005, the Hewlett Prize in Applied Sciences, the year 2000, UF Foundation STEM Professorship 2018, and NAE Excellence STEM Professorship, that's 2021. That's just beyond wonderful. And that's the person we have here on board with us today to speak to us. So I'm actually amazed, and I'm sure a lot of us are amazed. So, right. So while we continue, we can go on to share the link to every researchers that we know out there that we are sure that we don't want them to miss what today's topic of discussion. Now, to the next thing on our agenda, which is why is here with us today, Is here to talk with us about the topic, the transportation. And I'm sure that we all as eager as I am, right? So one thing I just want to ask us is, whilst is discussing, if there's any question that comes to mind, we can pen it down. And then we should know that this session is actually being broadcasted on the YouTube already. So we are currently live. So if at all you miss any session, do not be bothered at all, as you can go back on the YouTube. That's the smart YouTube channel to revisit today's webinar, as well as every other webinar you might have missed in time past. So while we open the floor for Dr. Sheriff, I just want us all to just give him a reaction of a round of applause while he come on board and speak with us. Over to you, sir. Wow, I think maybe Doctor is having a, let me see. I know the profile is a long read. Let me just call his attention again. So, Dr. Sheriff, over to you, sir.
Yes, well, thank you very much. You have been extremely kind to say all these things about me. I really appreciate your being so kind, and
Thank you, sir.
it's my immense pleasure to be here with all of you. I am I just shared my screen. I hope you all see it. I'm going to now put it in the full screen
Yes, sir.
mode here, and let me see if I can get back on the. So you can all hear my audio. Okay, is my audio um, getting through?
Very, very
Okay,
clear, sir.
excellent. And you see my screen, so I'm just going to go ahead and start. The hydrogen energy system and sustainable transportation is the title that I would like to talk about today. Um, of course, the hydrogen energy system has been introduced back in the 1970s by the late Professor Nejat Vezoroglu, who is considered the father of hydrogen energy. He established the Clean Energy Research Institute at the University of Miami. In 1974, he ran a conference called the Theme Conference in Miami Beach, Florida, where he introduced, along with others, they call themselves the hydrogen romantics. That group of people actually sat down in a room and talked about what would the life be like if we had a system where hydrogen is the energy carrier, and in this case, as you all know, when hydrogen is combusted, it produces water vapor. That's there's no carbon footprint, and it just produces traces of nitrogen oxides, very small amounts of them. But other than that, it's pretty safe in the sense that the carbon footprint is basically zero. And then in 1976, they established or I should say, Dr. Veziroglu established the International Journal of Hydrogen Energy. It was 4 issues that time, four small issues per year. It was published by Pergamon Press, which was later purchased by Elsevier. And the journal kept growing from 4 issues to 6 issues to 8 issues to 12 issues, and then it went to 15 issues per year, and then to 18 issues per year, and then to 24 issues per year, and then to 36 issues per year, and then to 52 issues per year. And it went all the way, and now it's 100 issues per year. It's published 100 issues per year, somewhere in the vicinity of between 45,000 and 50,000 pages every year of hydrogen research. Of course, hydrogen back then was not very popular. Nobody knew much about hydrogen energy. Now there are tens of thousands of researchers worldwide that are working on hydrogen energy. So now we are talking about how we can use hydrogen for the transportation sector, what we call sustainable transportation, and that's going to be the focus of some of the things I'm going to discuss today. So here is an outline. First, I would like to introduce hydrogen to you in a slightly different way. We're talking about the 2 types of hydrogen, the orthohydrogen and the parahydrogen. Many of us do not know that. In fact, there are 2 types. We'll get into that in just a second. Then we're going to talk about the challenges in after you produce hydrogen, what do you do with it? I'm not going to emphasize the production methods of hydrogen, but I'm going to emphasize the usage of hydrogen and the storage of hydrogen and how it can be used in both stationary applications and vehicular applications. And then I'm going to give you a conclusion at the very end. First of all, let us discuss the different modes of storage. Hydrogen can be stored either physically or chemically. If you look at the physical storage, you could have it in the form of compressed gas, or in the form of liquid storage, or in the form of cryocompressed storage, which is a form of gaseous storage, but under cryogenic temperatures. And then the slush hydrogen would be the last mode of physical storage, which would be basically a combination of liquid and solid, similar to what you get when you have slush lemonade, for example, when you basically have some lemonade and you sort of get the juice within the ice. So that would be the slush. In the chemical storage, you've got hydrides, which are different types. There is the hydrides or metal hydrides and the complex hydrides and the chemical hydrides, and then the interstitial metal hydrides. These are all different types. And the idea of a hydride is basically it's a solid metal or alloy that can absorb hydrogen or release hydrogen, depending on whether you do cooling or heating. If you heat a metal hydride that has hydrogen in it, or a complex hydride or a chemical hydride, any of those, by heating, they release hydrogen, and by cooling, they absorb hydrogen. And then we go to the other type of chemical storage, which would be either adsorption, liquid organic carriers, reformed organic fuels, or hydrolysis. These are all different types of chemical storage that are not hydrides. Now, I'm going to focus more on the physical storage for this lecture, and predominantly, I'm going to focus on the gaseous storage, the liquid storage, the cryocompressed gaseous storage, and then the slush I'm going to talk briefly about. Just to give us an idea of what it is that we're looking for a large gravimetric density and a large volumetric density. The larger, the better. So if you look at the table in front of us here, that table actually is showing two types of storage, or two types of densities. The gravimetric density is the one on the left, and then the volumetric density is the one on the right. And then I'm showing you different size storage doors. In this case, you either have large volume storage that would be between, let us say, 100 meter cube to 10,000 meter cube, whereby the stationary small storage would be under 100 meter cube, and then the vehicular storage would be under 0.5 meter cube. So it would be somewhere between 0.1 and 0.5 meter cube. So in one of those, depending on which type of storage you're dealing with, you need to be looking at the following numbers. For example, an underground storage for large volume storage is the volumetric density is not too bad. It's between 5 and 10 kilogram per meter cube. For the cases of the pressurized gas storage with above ground, in this case, the volumetric storage is between 2 and 16. Okay, so again, it's a slightly different range. There is an overlap, a little bit of an overlap. If you look at the metal hydrides, you actually get a large volumetric storage or volumetric density between 50 and 55, but the gravimetric density is very small, which is not good for the metal hydrides. And we're 0.013 to 0.015. That's not very impressive. Now, if you compare that to the liquid storage is going to give you 1, which is several hundred times more than the metal hydride and the pressurized gas storage. And not only that, for the volumetric density, you also have 65 to 69, which is significantly larger than any other mode. So the liquid storage is very attractive in that sense, because you give you the large gravimetric density and the large volumetric density. Now, if you go to the stationary small storage, you're looking at, again, the liquid is giving you 65, the metal hydride between 50 and 53, and the pressurized gas cylinder is about 15. And then the gravimetric storage, again, is not super impressive. Even for the liquid, it's 0.15 to 0.5, and partly because of the size of the door in this case. And if you look at the vehicle tanks, which are very small, then everybody loses, again, on the gravimetric side. On the volumetric side, the liquid and the metal hydride are significantly higher than the pressurized gas cylinder. Now, let us talk about the types of hydrogen that we are dealing with. There is, as I said, orthohydrogen and perahydrogen. Now, orthohydrogen, the nuclear spin is in the same direction. You see on the left side of the top left part of that slide, the orthohydrogen molecule, which has two atoms in it. The two atoms are actually where the nucleus is rotating in the same direction. So in this case, that produces orthohydrogen. And the other one, which is the perahydrogen, the nuclei are rotating in opposite directions. Now, the orthohydrogen is less stable than the perahydrogen. The orthohydrogen is the more unstable form of hydrogen. And eventually, if you have orthohydrogen over a long period of time, it will transform itself into perahydrogen. It will also transform itself into perahydrogen in the case of refrigeration. When you cool it, like when you're trying to liquefy hydrogen, you're going to cool it. And during the liquefaction process, the orthohydrogen will also convert into perahydrogen. And we want perahydrogen, we do not want orthohydrogen. The normal hydrogen, which is available at normal temperature and pressure, is 25% ortho, is 75% ortho and 25% para. 75% ortho, which is the bulk of the hydrogen will be in the ortho mode, and the 25%, a quarter of it, will be in the para mode. When the transformation takes place from ortho to para, it's an exothermic reaction, and as a consequence, that exothermic reaction results in the release of heat, which is used to vaporize the liquid hydrogen. So that's not a good thing. And as a consequence, what they typically do is they use catalytic converters to transform hydrogen during the liquefaction process from ortho to para. In other words, they can speed up the process of converting orthohydrogen to perahydrogen. That way, when they reach the liquid hydrogen temperature, which is 20.3 Kelvin, you are looking at 99% para and maybe 1% ortho, or sometimes even less than 1%. You want to get it predominantly and overwhelmingly in the para mode by the time you reach the liquid hydrogen temperature, in order to stabilize the process and make sure that the liquid remains as liquid. We don't want the liquid to vaporize simply because of the heat of reaction, or the heat of conversion that would ensue when the transformation takes place. Okay, so that is essentially the story on that. There are other differences between the orthohydrogen and the perahydrogen in the form of the spin alignment. Like you got the parallel spin alignment for the orthohydrogen and anti-parallel for the perahydrogen. Then the nuclear magnetic resonance spectroscopy, the so-called NMR, is triplet for ortho and singlet for para. This information, you can get some more information from the institute, where I cited here at the bottom of that slide. We would be remiss if we do not talk about the Joule-Thomson coefficient, in the sense that we are refrigerating and liquefying hydrogen. In the process of doing that, we're going to use a refrigerating machine, a cryogenic refrigerator, cryogenic liquefier, which is going to necessarily have what we call expansion valves. These expansion valves sometimes are referred to as the Joule-Thomson valves, or a Joule-Thomson valve, or an expansion valve. Sometimes they call them throttle valves. And a throttle valve, expansion valve, Joule-Thomson valve, all they do is reduce the pressure as the fluid goes through the valve. They reduce the pressure without producing any mechanical work. Unlike the expander, if you're dealing with an expander, which is the opposite of a compressor, the compressor raises the pressure, the expander lowers the pressure. In the case of the compressor, you perform work in order to perform the compression process. In the case of expander, you get work back due to the expansion process. That is not the case in the case of a Joule-Thomson valve or an expansion valve or a throttle valve. You only get the pressure drop, you do not get any work back. So that's the downside of that valve. But the upside is that it's cheap. The upside is that you can get those for a few dollars relative to getting an expander, which could cost you several $1,000s. Now, the reason I mentioned the Joule-Thomson coefficient, which is thermodynamically defined by this equation here, it's the partial temperature with respect to pressure at constant enthalpy, which gives you, when you analyze this, it gives you the term on the very right side of that equation. But what is important here is that this process is done isenthalpically. When if you're familiar with the first law of thermodynamics for an open system, and you apply it on an expansion valve, what you're going to find is that the only term on the left-hand side that would remain, and the only term on the right-hand side that would remain is the enthalpy. The enthalpy of the inlet of the fluid would be at the left-hand side, and it would be equal to the enthalpy of the fluid at the exit of the valve. So it's an isenthalpic process, assuming that there's no heat transfer, which the heat transfer is very small because the process happens very fast. And there is no work, of course, because there is no device that produces work or consumes work in the valve. So you end up having the inlet enthalpy equal to the exit enthalpy, and you end up with an isenthalpic expansion process as a consequence. Now, when you reduce the pressure, thermodynamically speaking, you are allowing the molecules to be farther away from each other. When the molecules are farther away, in other words, you increase the intermolecular distances. By increasing the intermolecular distances, you are essentially reducing the pressure, and vice versa, right? So reducing the pressure means that you reduce the likelihood of the molecules colliding with each other and colliding with the container walls. And that, as a result of that, you basically are going from a small space to a bigger space. So you end up with a bigger volume at the exit of the valve. Now, when that happens, normally for all fluids, or shall we say the overwhelming number of fluids, would be that the temperature will also drop. When the pressure drops, the temperature drops. Now, that is the case for hydrogen as well, except that there is a region whereby the reduction in pressure is going to be associated with an increase in temperature and not the other way around. And that is what they call the inversion temperature. And that temperature is very important, about 200 Kelvin. If you look at the, let me see if I can, my computer is just taking its precious time here. Let's wait a second. Okay, I moved back too far. Let's go back. Okay, so let's go forward now. So here the inversion temperature is the temperature at which a gas changes behavior during a Joule-Thomson expansion. Below this temperature, the gas cools upon expansion, while above it, the gas warms up again upon expansion. For the case of hydrogen, this temperature is relatively low. The temperature rise is relatively low compared to gases like nitrogen and oxygen. And I should say the temperature where that happens is about 200 Kelvin relative to 621 for oxygen, for nitrogen, and 764 for oxygen. So the idea here is that the hydrogen low inversion temperature arises from its weak intermolecular forces, which basically are associated with higher temperatures, repulsive forces dominate during the expansion, increasing the kinetic energy and the temperature. This makes it lower than the cases, let's say, for hydrogen, for nitrogen, and for oxygen. But basically, when you look at the inversion temperature curve, you will see that the solid line, where that's the higher inversion temperature, and then the dashed lines is the lower inversion temperature, and then the region in between is where cooling always occurs. It should be occurring in this region. Anything outside this region is going to result in an increase in temperature, which is not what we want. And it also it can raise issues with the safety issues, because if your temperature rises, generally speaking, you could reach the ignition temperature, and that could cause problems. But luckily, for the case of hydrogen, an expansion that results in a pressure drop of 10 megapascal, which is a good amount of pressure drop, is going to only raise the temperature by about 3 Kelvin, which is not significant enough to make us worry about. Now, what I'm going to do is talk about the issues that are under research right now that are making the usability of liquid hydrogen, slowing down the process of being able to take advantage of using liquid hydrogen. See, these are some of the challenges. The ortho-para conversion, I already talked about that, whereby the process is an exothermic reaction that results in heat release. So that is something we have to find a way to deal with. And of course, we use catalytic converters to speed up the process. The heat leak is another issue, which is when you store liquid hydrogen, any heat transfer from outside is going to result in vaporization of hydrogen, or what we call boil off is the term that they use. Thermal stratification is also a problem, in the sense that if you look at the liquid hydrogen tank, like for example at the NASA Kennedy Space Center, when you go and see this big spherical tank with the word H2 written on it, what happens is that the hydrogen gets stratified, whereby in the vicinity of the walls of the container, it would be warmer than in the bulk, in the middle part of the tank. And also it will be warmer at the surface of the liquid inside the tank. And there will be convection currents as a result of this thermal stratification, whereby the movement of the molecules of the particles of hydrogen is going to keep going up and down, because of when the temperature goes up, the density goes down, and then the hot liquid would have a tendency to want to go up, and the colder liquid has a higher density, so it has a density to stay in the bottom part. But because of the stratification, the movement continues, and that results in overall boil off as a result of that self-pressure, as a result of the thermal stratification process. So that's also something that we need to minimize inside the door. The self-pressurization is also a problem, whereby the liquid boils off at the surface, and the amount of vapor, hydrogen vapor, becomes larger and larger as time progresses. And when that happens, the pressure builds up over the surface. And when the pressure builds up, you could get to a point where the hydrogen would leak from the inside of the tank to the outside, because of the higher pressure that builds up. Okay, so that's also a possible challenge that we need to deal with. Sloshing is whereby when you have liquid hydrogen inside a tanker truck, and the tanker truck comes and stops at a stop sign or at a traffic light, and then moves after the traffic light turns green, and then stops again at another traffic light, and then moves. What happens is the liquid keeps moving back and forth between the front and end inside that tanker truck. In other words, in the tank itself, the liquid keeps moving, and as it moves it hits the front and the back of the tank. And when it hits the front and the back of the tank, it converts into the kinetic energy, converts into thermal energy. And that thermal energy is also used to vaporize hydrogen. So when the truck is moving, it has a certain kinetic energy. It stops all of a sudden. The mass times the velocity of that mass of that liquid is going to be converted into thermal energy, because it's kinetic energy. You are forcing the stop. You are forcing the liquid to stop. So that all that energy has to go somewhere, and thermal energy is the most obvious mode of conversion there. Lastly is flashing. And flashing happens when you are transporting hydrogen, or shall we say liquid hydrogen, from let's say from a source. Let's say that you have a big tank, and you wanna load hydrogen from the tank, or unload hydrogen from the tank into a tanker truck. In order for you to do that, the pressure at the source, which is going to be, let's say, at the stationary tank, is going to have to be higher, slightly higher than the pressure where the hydrogen is going. In order for the hydrogen to move, it has to move from the high pressure to the low pressure. And as a result, what happens is that when it reaches the destination, so it goes from the high pressure source, and when it reaches the destination into the lower pressure sink, what happens is hydrogen flashes off, meaning that the liquid that you're transporting, a portion of it is going to convert into vapor. And as a consequence, you are going to lose some of the liquid that you are transporting. That could be as little as 1 or 2%, and it could be as big as 15 or 16%. So depending on many things, and I'm going to get to that towards the end of the lecture. If you do it too fast, if you use pumps, for example, and transport hydrogen from the source to the sink, you're going to actually speed up the process of the flashing process is going to be more significant. Okay, so if you do it slower and maybe without pumps and maybe gravitation, and where you use other ways to move the liquid, just rely on the pressure difference, that would result in lower losses in terms of the flashing effect. So I'm going to skip these slides because I basically summarized all of those to you in my conversation here. I'm going to go to this slide whereby we have the 5 different types of storage modes in the form of either gas or liquid. And they have labeled them in this particular study by Argonne National Laboratory, which was published in the references given at the bottom there, World Electric Vehicle Journal in 2024. You will see that you have the liquid hydrogen, which is number 1, and then you got the subcooled liquid hydrogen, which is labeled number 2. And then you have the cryocompressed hydrogen, which is labeled number 3, and then the compressed hydrogen gas at 70 megapascal, which is labeled number 4, and then the compressed hydrogen gas at 35 megapascal, which is compressed hydrogen gas number 5, the category number 5. You will see actually on a pressure density diagram, you will see where every case exists. Now, what we want to do is we want to be at the very bottom and at the very extreme right side of this figure. Okay, the more on the right side we are, and the lower we are, the better off we are. And in fact, if you look at that, if you look at the extreme right corner of that figure, of that frame, you will see that number 1 is the winner, is the big winner. Number 1 is liquid hydrogen, as we all expected that to be the case. Why is that? It's because it's a high density at low pressure. High density at low pressure is good. Now, high density at high pressure is number 3, which is cryocompressed. Cryocompressed is high density at high pressure. It's giving you 72 kilogram per meter cube. That's great. But you know, look at liquid. Liquid is giving you 50 to 60 kilogram per meter cube without having to go to that high pressure. 30 megapascal is very high. It causes issues with safety. Of course, 70 megapascal is much higher than 30 or 35, and it is also more, it's going to require a pressure vessel, a much more expensive pressure vessel, and it's a heavier pressure vessel as a consequence. So it's cost and weight. And weight is going to make the car consume more fuel per mile than otherwise. So 1 and 3, the liquid hydrogen and the cryocompressed, and of course in between them is number 2, which is the subcooled liquid hydrogen. Now, subcooled liquid hydrogen is liquid hydrogen, whereas cryocompressed hydrogen is gas hydrogen. It's gaseous hydrogen. So it's very important to make that distinction. Now, again, it's giving you the pressure and temperature associated with every mode. In the case of the subcooled liquid hydrogen, you're looking at a pressure of about 1.6 megapascal. That's only about 16 times the atmospheric pressure. Atmospheric pressure is 0.1 megapascal. So 16 atmosphere is high, but not anything to be too concerned about. The density is 62 kilogram per meter cube. It's actually almost the same or slightly better than the liquid case. Of course, you've got subcooled liquid. But in the case of the subcooled liquid, in this case, the temperature is 28, whereas in the case of the liquid hydrogen, you're looking at, depending on the pressure, you could have anywhere from 26 to 30 Kelvin for the temperature. Of course, the liquid hydrogen temperature is, at normal temperature and pressure, is 20.3 Kelvin. But remember that we have 2 knobs in our hand. We have the pressure knob and the temperature knob. We can increase the pressure and decrease the temperature. If we do that, then we are making the 2 knobs work in the same direction. Increasing the pressure makes the molecules closer together, and therefore more likely to be more liquid. And lowering the temperature also makes the molecules closer together because the intermolecular distances are going to shrink. And as a result of that, the molecules are going to get closer together, meaning that they'll be more likely to be in the liquid form. So if you could what we call relieve one of those, in other words, only play with one knob and sort of make the other knob not as strict, then you're going to require more of that knob. If you only rely on the pressure and no reliance on the temperature, you're going to have a much higher pressure than otherwise. If you only rely on the temperature and not rely on the pressure, you're going to have a much lower temperature than otherwise. So those 2 knobs are essential to understand how they work. Now, for the case number 4, which is compressed hydrogen gas, and case number 5, which is also compressed hydrogen gas, the difference between 4 and 5 is only in the pressure of the gas. It's 70 megapascal for 4 and 35 megapascal for 5. Of course, this is a semi-log scale, so you will see that the difference is not huge. It doesn't look very much between them on graphically, but it actually is significant if in terms of the log. The vertical axis is a log scale, so it is significant. It's double the amount, 35 versus 70. Of course, again, I mentioned the problems with higher pressures. The higher pressures are more expensive doors, heavier doors, and they result in, if God forbid you have an accident, then it's going to be more catastrophic than the 35. So 70 is more dangerous to have. We try to avoid that if we could. Here's the, if you look at the subcooled liquid hydrogen fueling process is described in this slide. It's showing the subcooled liquid hydrogen truck on the left. It's showing the liquid hydrogen tank in the middle, and it's showing the liquid hydrogen trailer on the right side. So it's kind of giving you an idea of what is involved here, giving you, if we have, let's say, from 400 to 500 kilogram per hour, in the case of filling, the filling rate, the fueling time, and they're going to take about 10 to 15 minutes. The energy demand is giving it to you in terms of kilowatt hour per kilogram of hydrogen dispensed. 0.05 is really not too bad. The station footprint is going to be about 50 meters square of surface area without the dispenser, and the storage tank size we're looking at about 4,000 kilogram per liquid hydrogen in 10 hour of fueling. And then the fueling modes is parallel and back to back in this particular study. This is published in the World Vehicle Journal in 2024. And you got the reference here. You could read the paper if you want to. This is another slide showing the left-hand side is showing the flow, pressure, and temperature profiles during the subcooled liquid hydrogen fueling process. And the right-hand side is showing the pressure temperature plot of hydrogen during in general, whereby you look at the pressure temperature relationship. And here, of course, you're going to see all the different zones. You got the solid zone, the liquid zone, the vapor zone, and then the supercritical zone. By the way, I just wanted to emphasize a point that in order to and this is the difference between a vapor and a gas. Okay, here sometimes we talk about vapor hydrogen, sometimes we talk about gaseous hydrogen, and this is not a trivial distinction here. It's an important distinction. Gaseous hydrogen technically exists in the supercritical zone. Okay, that's gaseous hydrogen. Only exists in supercritical conditions, meaning that the pressure of gaseous hydrogen has to be larger than the critical pressure of hydrogen. If you are larger than the critical pressure of hydrogen, you are gas and you're not vapor. If you are below the critical pressure of hydrogen, you have three different possibilities. You could be vapor hydrogen, you could be a mixture of liquid hydrogen and vapor hydrogen, you could be liquid hydrogen, you could be solid hydrogen. All of those are below the critical pressure. I have to sort of correct myself here, because in the way I'm sort of ignoring the effect of the temperature. So because you have to have these two knobs, kind of coordinated with each other. Okay, and again, if you increase the pressure, you are allowed to increase the temperature a little bit. If you decrease the pressure, then your reliance on temperature is going to be more critical, and you're going to have a low enough temperature in order to have the liquid. So in this case, I have to sort of maybe be more careful in describing things. And here, in fact, you will see the density associated with each type. The density associated with each type, as you increase the pressure and you decrease the temperature, you're likely to have more density, larger density at moderate pressure. So here, for example, in the case of the red line, you can see the red line that is drawn. That red line is at temperatures in the vicinity of about 20.3 Kelvin or so. And the pressure is actually less than 1 megapascal. In other words, about 0.5 megapascal. 0.5 megapascal is about 5 atmospheres. Again, if you want to go to the 0.1 megapascal, which is the very bottom number, which is atmospheric pressure, you will see that you're going to hit about 20.3 Kelvin. It's appearing as if it's 20, but it's almost 20.3. Okay, you will see the solid line at the 0.1 megapascal pressure is hitting at 20.3 Kelvin. Now, if you look at the left-hand side is showing you three different things. The flow rate as a function of time, the pressure as a function of time, and the temperature as a function of time. The time, of course, is the filling time. This is the filling time for the door. You're gonna transport hydrogen or subcooled liquid hydrogen from the stationary tank into the, let's say, the trailer, the tanker truck. And in this case, you're going to see what happens is the temperature drops, maybe rises a little bit, and then drops a little bit, and then rises just a tad during the process. The pressure drops and then rises and then drops and then rises a little bit and then rises a lot. Okay, so these are the different stages. It's showing you where during the piping cool down stage versus the pressure corridor stage versus the main fueling step, or the very towards the end of the fueling, or the so-called steady state fueling process, which is the bulk of the time. In the middle, you can see that takes more time than any other stage. But again, you're going from a source into a sink, and in order for you to do that, you're gonna have to keep in mind that the pressure has to be higher at the source, and then eventually you could use other methods to have a higher pressure. If you have a smaller tank at the sink, and you put a certain amount of it, you could conceivably raise the pressure higher than the source. But in the transition process, the pressure has to go down in order for you to be able to make the transfer. And here the flow rate, you can see where the flow rate changes in the different phases. So again, my computer is just taking its precious time here, so we're going to go to the next slide. And I believe, okay, I moved a little too many slides here. Let's go back to this one. Okay, I believe this is the same slide that we were at. Let's go to the next one. That's the study that's done by Argonne National Lab on the onboard cryogenic hydrogen storage. I would like to just touch base briefly with you on this, because they did really some fantastic work in terms of heavy-duty vehicles in particular. And this was done in, they presented that work in a hydrogen workshop in 2024. And here they looked at different scenarios for the vehicular storage. Here they're showing you, for example, on the left-hand side, it's showing you the loading at the terminal. So you've got the storage tank, like a spherical tank, and then you're taking hydrogen from it, liquid hydrogen from it, and putting it into the trailer. So this is the loading at the terminal, and then you have the back to the terminal. You can see where the line is coming from the tank to the trailer through the valve, the fill valve, and then the vent valve. The vent valve is designed to relieve the pressure as needed, and that also is part of the safety precautions that need to be taken. Just to give some numbers, put some perspective here, you're looking at about 64,000 liter loading trailer terminal. The pressure transfer from the terminal is 24 psi. That's about 1.8 atmosphere to the trailer. The trailer is at 20 to 22 psi. Again, no surprise there. The pressure at the trailer is less than the pressure at the tank in order for the transfer to occur. 600 kilogram per hour is what you're looking at. Sorry, I need to get back here. Oh. Okay, and then for the middle diagram, you're looking at the door loading at the refueling station. And in this case, you're looking at a 12,500 liter door at the refueling station. And again, giving you ideas about the pressures and the flow rates involved. 60 psi from the trailer. The door is maintained at 45. In this case, you're doing the 60 to 45 psi. And because of the pressure difference is very large, there's 16% total boil off that includes 3% from the door during the loading and 12% from the final depressurization of the trailer to 20 psi, because you're going to eventually need to go to 20 psi. So all of that is going to result in a good amount, about 16% boil off losses. If you do a pump transfer you can actually accelerate this process, and you can also reduce the losses to about 3.4%. That would be from the door and 0% from the trailer. So it makes sense to use a pump in this case. And then the last diagram you can see at the bottom here, that's the refueling of the truck to the tank. So you've got it showing was using the pump. It's showing the pump there to accelerate the process. This is another slide showing the particularly for heavy duty trucks. They did again they looked at the liquid hydrogen, which they actually called it liquid hydrogen 1 and liquid hydrogen 2. Liquid hydrogen 1 is with onboard pump, and liquid hydrogen 2 without the pump. And then you have the cryocompressed hydrogen, that's case number 3. And then you have the subcooled liquid hydrogen, which is case number 4. Okay, and they're showing you the diagrams, the plan of what is involved here, looking from the top of what is involved and who is giving hydrogen to whom, type thing. And then it's showing you the availability of different pieces of equipment. For example, here you got an onboard pump is available only in the liquid hydrogen 1, and there is an intact heat exchanger. It's available in all of them except the liquid hydrogen 1. And then you're looking at the different values of the pressure, the operating pressure, the allowable heat gain, and the minimum dormancy, again, giving you the numbers for every one of those cases. Every one of those, by the way, has a reference, and it's given by them at the bottom here. They published this work, International Journal of Hydrogen Energy. I believe 3 of those are published in International Journal of Hydrogen Energy, 2023, 2023, and 2018. And then there is one published in CEP Heavy Duty Event, or presented in that event in 2021. This is another slide showing the hydrogen storage volume involved as a function of the tank volume. And for all the different 5 cases that we mentioned here, I don't want to bore you to death here on that. You can actually have that slide and look at it. This is the vehicular storage, the usable storage density, again, giving you what it is for every case. You can see, of course, the density for the 700 bar, or the 700, the so-called 70 megapascal. It's about 700 bar. 1 bar is 1 atmosphere. So basically about 700 atmosphere versus 350 atmosphere for the compressed hydrogen. And then for the subcooled hydrogen, the cryo-compressed hydrogen, and for the liquid hydrogen 1 and liquid hydrogen 2, with and without the pump, it's giving you the density, the usable density. And all of them are very impressive. Of course, the gaseous are the lowest, which not surprisingly. So, and then they're plotted in the diagram below. Here is the gravimetric capacity, again, for every case, 19% and 16.6% for the 2 cases of liquid hydrogen. For the subcooled liquid hydrogen, 16.4, the cryocompressed 9.8, the compressed hydrogen at 35 megapascal is 7.2, and then at 700 is 5.7%. This is the gravimetric density, the gravimetric capacity for every case. And then the volumetric capacity is given here in terms of gram of hydrogen per liter. The gram of hydrogen per liter, it's more like a kilogram of hydrogen per meter cube. Similar numbers. And then the cost, which is, of course, in the end, that is the very important factor to consider. You're looking at the cost, and here the way they presented the cost is they presented it in terms of for every one of those cases, they gave you the total cost per kilowatt hour. They gave you the cost of the carbon fiber composite percentage, and the liner percentage, the system testing percentage, the vacuum insulation percentage, the outer shell percentage, the housing support and assembly percentage. All of those are breaking them down in terms of dollars. Use all of those are dollars. So, for example, if you take the compressed hydrogen case at 350 bars, you're looking at $12.66 the total cost, and then $3.4 for the liner, 77 for the carbon composite is the 77%, 3.4% for the liner, 0.7% for the system testing and so forth. So some of those other things don't cost anything, like vacuum insulation and outer shell. They're so small that they're not written for the compressed hydrogen. But then they have values for the liquid hydrogen 1 and liquid hydrogen 2, the cryocompressed and the subcooled liquid hydrogen. They have values that are not zero. And then here, the future outlook, this is, I think, the last slide. The future outlook is that they indicate that cryocompressed and subcooled liquid hydrogen are attractive on board hydrogen storage options for heavy-duty trucks if the fuel cell system accepts hydrogen delivered at 5 bars. And then the cryocompressed is the only viable liquid storage option if the fuel cell system requires hydrogen to be delivered above 15 bars. The low-pressure liquid hydrogen storage becomes competitive if onboard boost pumps capable of delivering 16 kilogram per hour of hydrogen at 5 to 15 bars pressure are developed. The stationary pumps are capable of transferring liquid hydrogen from the trailer at 1100 kilogram per hour and providing 5 bar of pressure can greatly reduce hydrogen losses during the doer loading. And the future study to assess the potential of eliminating hydrogen loss from the door with the cryocooler is actually needed. So those are all the summary of the study. In conclusion, I can tell you that there is a good amount of effort going on, and especially at the Department of Energy. There was a time, at least, when they were extremely active, and they continue to support hydrogen. The cryocompressed hydrogen, the compressed hydrogen gas can only reach storage densities up to 40 kilogram per meter cube. And subcooled liquid hydrogen can reach up to 62 kilogram per meter cube at 16 bars and minus 245 degrees. And if you combine higher pressure and low temperature, you could get to 72 kilogram per meter cube. Okay. The storage technologies of cryocompressed hydrogen are more complex, and they actually at a lower technology readiness level right now. Although a friend of mine that used to work at Pacific Northwest National Lab is working on the cryocompressed, and he continues to pursue the technology. Today the compressed hydrogen at 70 and 35 are used in light duty vehicles and for buses. So with this, I conclude my presentation. I'll be happy to answer your questions. So thank you very much.
Thank you very, very, very much, sir, for such wonderful ride of knowledge, actually. Yeah. And I'm sure it's the same thing for every one of the listeners here today. We all have actually learned a lot from actually this presentation. From last presentation, we were thinking about hydrogen types in terms of the source of production only, whereby we were able to categorize them in terms of color, brown hydrogen, that's hydrogen from fuel, that's the one from like refineries. We have the blue one and the green one, and then now we are here today, we are learning it in terms of the auto para dynamics, understanding the conversion from auto to para and the need for it to exist in para. Such incredible ride of knowledge. And then the storage form, that's the liquid, the compressed gas, and every other thing, the subcooled liquid is actually wonderful. It's a wonderful unraveling of knowledge from you, sir. And we are very, very appreciative of it. We are very, very appreciative of it. And I'm sure that there should be a question by now. But because of our time, please, I would like to let us know that we are only allowing 3 questions. If we can get 3 questions, then that would be good. So if you have any question, just kindly react, and then I'll give you the stage to ask your question. Thank you.
Thank you very much, the moderator. I want to appreciate Professor Sherry for that wonderful presentation. And I believe that everyone here, as researchers, as students, so very much equipped by the volume of the presentation. And then while we're waiting for questions, as the moderator has mentioned, I just want to ask what you will advise, looking at Africa particularly now, how to get started. I know from your presentation, the US, there are a lot of work ongoing presently, different people working on different type of hydrogen, whether it's cryo, or sub or liquid, so what will you advise given the peculiarity and where Africa is in terms of technology and readiness, the entry point for whether PhD research, level or as a research group, particularly what we are presently doing now at SMART, getting started in terms of, looking at a plausible area to really, invest the time. So have you ever looked at Africa in terms of collaboration, in terms of where you will want to encourage, us to start from? Quick before we have a question from the audience.
Yeah, I mean, for Africa, Africa is in an excellent position, geographical position, to have a hydrogen economy. A good amount of Africa is, the sunshine, the solar resources are very high compared to other places on the globe. So Africa is in an excellent position to combine what we call the solar hydrogen energy system, where we use solar energy as a primary energy source to produce hydrogen from water electrolysis. Water electrolysis is, in my opinion, it's the way to do it if coupled with solar energy. Because if you have high efficiency solar cells, which we do now, we have high efficiency solar cells, you could use the electricity generated there. Now, some of those high efficiency solar cells can reach 36 to 40% efficiency. Some of the concentrated, the so-called CPV, or concentrated photovoltaics, can have a good efficiency. They can produce a lot of electricity, free electricity, essentially, to electrolyze seawater. I would like to think, I don't want to touch the freshwater resources because there is very limited supply of those. But then we have been blessed with 71% of the surface of the earth is essentially seawater. Okay, so we're looking at a huge supply of essentially unlimited seawater that keeps getting replenished, by the way, from the rain. So it's not like we're going to use it and then we're going to deplete it. It's going to be there forever, essentially. And seawater is good. It doesn't rot. It is the only downside of seawater is that the high concentration of salt would make corrosion a problem. But there are ways to deal with corrosion. So we can deal with corrosion. We can use seawater, solar energy with seawater, electrolyze a lot of seawater, get a lot of free electricity, use that free electricity to produce a lot of hydrogen. Okay, so we're gonna electrolyze water. You have hydrogen and oxygen, two very highly demanded, highly needed, highly treasured commodities. Because you take them and put them into a hydrogen fuel cell in the car or in the bus, recombine them in a fuel cell, and produce electricity that drives the car. So you do reverse electrolysis in the car, and you do electrolysis in the production plant, the photovoltaic solar plant. You produce the electricity, you electrolyze water there, and then you take those two, put them into a car with a fuel cell to recombine them and produce electricity that drives the car. Now, you don't have to deal with a battery because the battery is I mean, it's right now I like batteries, but I do not want to deal with the dispensing the battery. And in fact, now we are at the point where companies, where customers who buy electric cars are basically dumping their batteries, in many cases, in an unsafe way, and in violation of there are not enough laws yet in the country to ban them, but there will be laws that will ban just dropping your battery in a dump site. So because it has some dangerous elements, it has some toxic elements, and it has to be dispensed with in a correct way. So batteries are not the long-term solution. I hate to say this, but they're not the long-term solution. They're a good solution right now. Batteries also have a carbon footprint at the production side, so they do produce hydrogen. They do produce carbon footprint when they're produced. They have zero carbon footprint when they're used, but they are heavy on carbon footprint when they're produced. So we have to be careful about that. But again, hydrogen fuel cells, in my opinion, are the way. Solar energy and seawater, solar energy, and fuel cells. That's the solution. Now, there are also efforts right now. I know there is an Australian group in Western Sydney University in particular, one of the most famous professors there, who is a leader in surface defect chemistry. And he is working with his guys on producing engineering new surfaces to convert more electricity from the solar cell. In other words, make the solar cell produce more electricity per unit surface than otherwise, by actually custom making a new material based on surface defect engineering. They have what they call the high temperature electron probe, which is a unique device that gives you that can be used in situ to actually tell you exactly how the surface chemistry is reactions are going on, and as a consequence, you are able to actually custom make the material that makes more electricity come out of that. And you can use the same technology at the fuel cell to actually custom make the same material that is being used for the solar cell can also be used for the fuel cell. In other words, you are winning on both ends. You're winning on the production of electricity, and you're winning on the use of the electricity that you produce. So again, that's just my vision of things. I'm sure there are other opinions. I don't want to monopolize. I say my opinion is the best opinion. I'm not saying that. I'm just saying this is one thought that I think is very promising. Okay, so we need to have the political will to move in any one of these directions. Okay, and I think electric cars, batteries have been successful in part because of the government support. And we need some government support, because the private sector may not be able to do this in the beginning. I mean, eventually they will be able to catch up, but the private sector is only limited, and they need the big profits right away, and that's where government comes in, because in those cases there's no big profits right away.
Okay, thank you very much. So, moderator.
Yeah. All right. That was actually very, very splendid. In all honesty, it pinpointed every other thing. So, please, if you have any question, this is the time to ask. This is actually the best time to ask. So, if there's any question, before I go forward to put forward my own personal question, any question from our end, you can react, and then the floor is yours. Just raise your hand, and the floor is yours. Okay. So as it seems, I'm not sure if we'll be getting questions from the audience for now, but let me go on to ask my questions, sir. First of all, I want to say thank you for the wonderful presentation you gave us today. And you did already highlighted my question in some parts when you mentioned the fact that the hydrogen generation via electrolysis and then reversing of the electrolysis is what gives us the electricity utilized in the cars, right? My question is around the shortage, the utilization of hydrogen in sections like in other sections apart from transportation generation, transportation help, right? Because it has to be promising in other industries. Say, for example, the metal production industry, which produces a whole lot of CO2 also. So I want to ask if there's any research pertaining utilization of hydrogen as an energy carrier in other work-intensive industry like the metal production industries. So that's the basis of my question, sir.
Yeah, you're basically saying is what are the uses of hydrogen in the manufacturing sector, especially in the metal industry manufacturing sector? I presume that's your question there.
Yes, sir. Yes, sir.
So basically, hydrogen is an energy carrier. Natural gas is an energy carrier. Electricity is an energy carrier. Gasoline is an energy carrier. These are all energy carriers. They're not energy sources. Okay, energy sources is solar energy, nuclear energy, wind energy, coal. These are the sources. The carriers. So anytime that you have so the question I posed is, what do we use in the metal manufacturing industry as an energy carrier? If we use natural gas, or if we use coal, if we use nuclear energy, or if we use solar energy, any of these, we will be able to replace the carrier that we currently use with hydrogen. In other words, hydrogen is just an energy carrier. It can be used in a car. You can put it in your tank and combust it in an internal combustion engine, the same way you combust gasoline or diesel. You could do that, and there are people who have perfected the combustion chamber in a hydrogen internal combustion engine. Somebody like Professor Michael Swain at the University of Miami, who has been doing this since the 1970s. He's built 19 hydrogen prototype engines for Ford Motor Company. He's built lots of IC engines for Toyota and for Nissan. He knows how to do it, and that's a technology that's already known. It's perfected. We know how to build an engine with no knocks and anything. In other words, to make it just run as smoothly as a gasoline engine, as a diesel engine. So that's one aspect of it. Or you could use it in a fuel cell, like I mentioned before, where you could basically recombine oxygen and hydrogen in a fuel cell and produce electricity that drives the car. So that's also the other option. In the case of the industrial sector, you could use it the same way you use natural gas. You could essentially remove natural gas and put hydrogen there. Okay. Now you may have to make some modifications to the piping and all that because of embrittlement and things like that. But essentially the answer to your question is, anytime you have natural gas, anytime you have gasoline, anytime you have diesel, anytime you have any of these things, you could replace them with hydrogen. Of course, with modification of the infrastructure around.
Thank you very much, sir. Thank you very, very much, sir. So, please, if we still have any other question, one last question from us, any question from the audience before I go on to give the stage back to Dr. Emmanuel for him to speak to us concerning the next webinar, which is actually our last webinar for the pre-conference webinar before we start making active preparation towards the conference itself. So, any question? All right, so I believe there's none. So over to you, sir. Thank you.
Thank you very much, the moderator, and I appreciate everything that has gone into the preparation for the webinar for today. I want to especially appreciate Dr. S.A. Sheriff once again, and I really love the presentation and how we particularly can come in also smart in collaboration with what you do, the University of Florida. Personally, I've made it a plan to ensure I visit your lab in January when I come over, and see what we can do in collaboration with what you are already doing over there. In also collaboration with other speakers that have spoken to us about hydrogen 2 weeks ago. Okay, I think 3 weeks ago, yes. Professor Greg Natra actually opened the floor about hydrogen with what Canada is doing. Now we can see the taste to what the US is doing from what Dr. Sheriff has presented today. We just want to see what we can do in Africa as well, with what activities of SMART is pioneering, and how we can leverage on ensuring that we see technology that fit the African environment. And I believe that we would tag along as much as possible. So once again, thank you very much for your time. So for next week,
it's been a pleasure to be with all of you today. Okay. I really appreciate the invitation. Thank you so much.
Yeah, thank you very much too. So for next week, as the moderators has mentioned, we'll be having our 12th live webinar. Once again, the live webinar was strategically planned to ensure we just let participants know about the SMART conference hub from 8 to 24 October. So having a last webinar next week. That is the of the webinar energy management. We had HIT presentations on from research to realities. And so this webinar from Dr. Sharif is the third one on energy management. So we'll be having a speaker from the Energy Commission of Nigeria. And just while this conference was going on, this presentation was going on, I got a call from Energy Commission of Nigeria in Abuja that the speaker has prepared to give us the last presentation of energy management. Now, if we are very much aware of the dynamics of Energy Commission of Nigeria and their research centers, they have 6 research centers actually, and the centers that is focused on energy management is actually located at the University of Lagos. And I was privileged to be one of his director a few years ago, and presently the current acting director is actually my former PhD student. But he would have been the best person to make the presentation next week, but because of his schedules and engagement, so we decided to have the director on energy management from the headquarters, that is in Abuja, to make the presentation. So so we'll be honored to have him round up the live webinar. So I just want to let everyone be prepared to join us next week as usual. Thank you very much for your time. Thank you for the consistency, and we'll see you next week. Bye.
All right. Thank you very much for such wonderful remark and for the great update for the next webinar, which is going to be the last webinar. I'm guessing we are leaving the topic till we unravel it during the course of the week. To our wonderful listeners who are researchers, engineers, and energy investors, and to everyone who might have been viewing, also following up on YouTube and every other social media platform, we still remain the SMART project team, pioneered by Dr. Gedengbe. Yes, and we are happy to have you during the course of the webinar. We are most especially grateful to God, and we say a big thank you, Dr. Sherry, for being present here today, dispelling knowledge as much as you could. We are actually delighted to have you amongst us. So on that note, I'll be putting the webinar on the close for now till next week, actually, till next week, where we'll get to say our last goodbye for the pre-conference webinar ahead of the conference itself. So do have a wonderful rest of your day and a great weekend ahead. God bless us.